All right, the next section that we have is 4.5, L'Hopital's rule. So L'Hopital's rule, I know some of you know this already because it oftentimes gets used in the beginning of a calculus class by people who have seen a little bit of calculus before, but it's not always used correctly. Besides, in the beginning of calculus, we use a limit to define a derivative. And L'Hopital's rule is a way of using derivatives to evaluate limits. So earlier on in the calculus course, L'Hopital's rule, although it does make many limits much simpler, one, it's just not appropriate to teach it at that point because we're just defining what a derivative is using a limit. So to use a derivative to evaluate a limit would be inappropriate. Secondly, not every limit is going to best be solved by L'Hopital's rule. Just because a tool can do the job doesn't mean it's the best tool for the job. So, for instance, here with these four limits, all of these limits can be solved using L'Hopital's rule. For instance, well, let's go ahead and take a look at what L'Hopital's rule says. Essentially, what L'Hopital's rule says, and there's a little remark here that kind of extends the applicability of L'Hopital's rule, but effectively, if you have a limit where it just so happens that these two functions, as x goes to a, when you plug in a into them, you get 0. If that's the case, then you can go ahead and say that this original limit is equal to the limit of the derivatives. And if we go ahead and apply this remark here, we actually find out that it doesn't have to be just 0. We could also have infinity over infinity, one of our indeterminate forms, and then you could also use L'Hopital's rule. So as of right now, L'Hopital's rule works if your indeterminate form is 0 over 0 or infinity over infinity. Those are the two forms that you can use. Now, there are some other indeterminate forms that we can algebraically rewrite so that we do get 0 over 0 or infinity over infinity. And we'll talk about those later, but L'Hopital's rule is a very widely applicable rule if you have some sort of indeterminate form that can be changed into 0 over 0 or infinity over infinity. So let's take a look up here really quickly. So right here, we have a limit as x goes to 1. And if we plug in 1 here, we do see that we get 1 minus 1 over 1 minus 1, which is definitely 0 over 0 indeterminate form. So we could definitely use L'Hopital's rule here, and that would be a nice choice. This limit down here, if we plug in, again, I hate to say this, but if we quote-unquote plug in infinity, then we'll see that the top goes to infinity, and the bottom also goes to infinity. So this is of indeterminate form infinity over infinity. So L'Hopital's rule does work. We're clear to use it. That is the hypothesis we have to satisfy. So we could definitely use L'Hopital's rule here. But if you actually think about what's happening here is we have a 5th degree polynomial and a 6th degree polynomial. It would have to take us 5 derivatives for this function, this expression in the numerator, to lose its variable. Now these variables would die off after 2 derivatives. This goes to 0 after 1 derivative. This goes to 0 after 2 derivatives. This here, we'd have to do a lot of derivatives. We'd have to do 6 derivatives here to kill that. So, and each time we'd have to verify, do we still have infinity over infinity? So there'd be a lot of derivatives here. A better choice for this kind of expression is, because this is a limit as the variable goes to infinity, we can use dominating terms. So the better choice here would to just say, by the method of dominating terms, this limit would be, y goes to infinity, would be equivalent to 7y to the 5th over y to the 6th. Effectively, we're just picking off the dominating terms. Again, the method of dominating terms, you can only use that as you go to infinity or negative infinity. If you go to a finite number, such as this limit up here, that does not work. Up here, for this limit, if you plug if you plug in 4, you do get 0 over 0. So that does work out. But because L'Hopital's rule, you have to take a derivative. When you take the derivative of a square root, you can certainly do it, but the derivative of a square root typically gets uglier and more complicated the more derivatives you take. So depending on how a square root appears in your expression, L'Hopital's rule, although applicable, may not be the best route. In this case, I don't think it's that bad if you choose to use L'Hopital's rule, but it's something you should think about. Just because you can use it doesn't mean you necessarily should. And down here, for this limit, we can, of course, calculate this using L'Hopital's rule, because we do have 0 over 0. But we also know our trig limits. For instance, we know that the limit of this expression as theta goes to 0 would be equal to 0. And we also know that the limit as theta goes to 0 of sine of 0 over sine of theta over theta, or its reciprocal, theta over sine of theta, this goes to 1 as theta goes to 0. So we could easily rewrite this expression as 1 minus cosine theta over theta times theta over sine theta, and then in the limit, this goes to 0, this goes to 1, so the answer is just 0. Now, what takes more time, what takes more work? It kind of depends on how well you know your limits.